Very good, thank you, and thank you to all the organizers. It's been a great conference so far. Yeah, so this talk will be also on the same example of Hirzebruch that we saw in the last talk, but a very different sort of variation on what Hirzebruch did. And somehow the point is when somebody like Hirzebruch produces an example, you should think hard about it. So I'll recall the construction. And so I'll take theta to be e to the pi I over 3. And I realize in France it's a sin to choose a root of unity. But put your guillotine away. There's a reason. And so I'll take E will be C modulo Z adjoint zeta. No, pi I over 3. 6, yes. Oh, did I say third root? Yeah, sixth. Sorry. And on this, we'll have, I'll call them E0, E infinity, E1, and E zeta. And so E alpha will be the set of Z comma alpha Z sitting inside of A. And so this is the picture that came up in the previous talk. I'm actually going to draw this. And the point is I had to choose this one because for these all to intersect, so the E alpha pairwise intersect at the origin. And the point is, if I chose the other sixth root, that would not be true. So the point is you count the number of intersection points by the difference between the slopes. And this is the one that makes it a unit when you take 1 minus zeta. And so we'll take, I'll call it B, will be the blow up of A at 0, 0. And I will introduce some colors. So we'll have the exceptional P1, and then we'll have our curves E infinity, E0, E1, and E zeta. And then you take M to be B minus the union of the D alphas. And so this is some open manifold, and as Xavier mentioned, this is a bulk quotient. Oops, these are the proper transforms, sorry. These should be Ds. So D alpha is the proper transform of E alpha. And so what you notice is that these have self-intersection -1, and they're disjoint. And the reason for this is, so there's classically the Bogomolov-Miyaoka-Yau inequality that says C1 squared is less than or equal to 3C2 with equality if and only if you're a bulk quotient. But there's also a logarithmic version of this. And so you look at C1 squared of B with respect to D. So D here is the union of the d alphas, bless you. And this is less than or equal to 2c2 bd with equality if and only if kb plus d is nef and big, which we will recast at this conference to be Simpson, and you have equality. Okay, so now this goes up to the top. Oops. Oh, did I get the inequalities all backwards? Wait. Oh, the 3. I forgot the 3. Of course. I'm even not tall enough for that. Absolutely. So in this case, so C2 is very easy to calculate because I'm just removing some elliptic curves, right? And so C2, I'm taking something of C2 equals 1, and I'm removing a bunch of disjoint elliptic curves. So it's easy to see that C2 of B, comma B is equal to 1. And it's really not that hard either to see that C1 of this is equal to 3 because you want to look at KB plus D squared. And so you get minus 1 plus 4 is equal to 3.
Sorry.
Yeah.
So C1 log version says that there is equality if and only what?
Oh, it's a bulk quotient. There's no words there. You can't not see words. I didn't write them. If and only if you have a bulk quotient. It takes too long for it to come down, but yeah, open bulk quotient, yes. Yes, exactly. So as in the closed case, there's a nice certificate to say when something is. And what you see is that this is the Euler number of what I called M. And this is, of course, minimal. Minimal possible value. So great. In fact, there are some other things you can show. This gamma, this lattice is a congruent subgroup. Of an arithmetic group. This M covers 2 of the examples of de Lehmann-Mostow. And it has a bunch of other nice properties. Were there any others I wanted to say now? No, I think that's good enough. So one important question in the study of sort of locally symmetric spaces if you want to study they're Betti numbers, and so the first part of this talk, I'll talk about how you can get some interesting information about Betti numbers of bulk quotients from just this example and covers of it. In particular, and say give geometric interpretation. Whatever that means. Okay, so the first thing I want to do is I want to actually calculate the Betti numbers of M. And to do that, you need to know a little bit about the Cusp structure. Of bulk quotients. And these will always be smooth. I won't worry about orbifolds. So you have this open ball quotient. And so, just as in the Riemann surface case, it'll have a bunch of ends and then some compact garbage. And each end looks like n cross r, where n is a nil 3 manifold. So it's the quotient of nil 3 space modulo, we'll call it delta, for delta inside the isometry group of nil, which is isomorphic to nil semi-direct product S1. And the point is, when you realize this is as the Heisenberg group, you end up with things that look like 1, z minus z bar minus z squared over 2 plus. So this is the classic realization of this, and this is the S1 factor. Okay.
I'm sorry, who is isomorphic to nil product S1?
That's a homeomorphism. The end of this manifold is homeomorphic to n cross r, where n is a nil 3 manifold.
Yes. But then something is isomorphic to a nil semi-direct product with S1.
Isometry group with n. So n is a quotient of nil 3 space by some lattice in its isometry group. What's that? Oh, thank you, Fabrizio. He's my copy editor. So the point is, you say that delta is rotation free if there's no S1 contribution. So the point is, topologically, all of these nil 3 manifolds fiber over a 2 manifold. But it could be that it really is fibering over a sphere, and that's when this contribution comes in. So rotation free just means that when you realize these elements of delta as matrices, this C is always 1. And so this, in the arithmetic case, goes back to the book of Ash, Mumford, or say, and Mach showed that really everything they do works in the non-arithmetic case. So M B2 mod gamma is an open ball quotient with a lattice, torsion-free lattice, with all parabolics rotation free. This implies that M admits a smooth toroidal compactification by elliptic curves. And so what you see is this M lives inside of S, which is a smooth projective surface. And M is S minus some union, I'll write suggestively like this, where the D alphas are elliptic curves. Moreover, in this case, pi 1 of this n has a presentation of the form B commutes with C, and A, B is C to the minus K. So N is the N for some D alpha. Yes, yes, they are disjoint. Absolutely. And you know, somehow if you achieve equality in that log BMY inequality, that somehow I didn't assume that the D was a bunch of disjoint elliptic curves, but it actually follows from that. Then this implies that D alpha squared is equal to minus K. So I can in fact tell you, so the structure of this nil manifold, you see now the end is a punctured disk, that's gone. It's a punctured disk bundle over a 2 torus. And so to get the compactification, what you do is you plug in the puncture, and the way you do that smoothly is dictated by the holonomy of that nil manifold around the puncture. And so that's saying precisely that the normal bundle has that degree. Okay? So in particular, you apply this construction to Hirzebruch's example and you do exactly what I did on the top board. Okay? So Hirzebruch's. Construction is, I'll say, admits a smooth toroidal compactification, okay? Because it is exactly this construction. Okay. Smooth, yes, yes, precisely.
Which is a blown-up surface.
That's right, and so, yeah, so the smooth, and in fact, it's an abelian surface. Blown up once. Exactly. Okay, so back to Betti numbers and where all of this comes into the picture is, so maybe I'll call it a proposition. And I don't know if this case exactly appears in this old paper of Zucker's on homology of compactifications, but this is an old Inventiones paper of Zucker, and certainly all the ideas to do what I'm about to say are in the paper. So if M is B2 mod gamma and M admits a smooth toroidal compactification, maybe I'll call it S, that implies that the first Betti number of M is the first Betti number of S. And the proof is just graduate algebraic topology. So you have that M is equal to S minus some union of D alphas. And now you look at the exact sequence in homology. This will be S goes to direct sum over alpha, H1 of the neighborhood of D alpha goes to H1 of M plus the direct sum over alpha, H1 of, oops, this is the intersection. Yeah, see, I've failed my preliminary exam. Neighborhood of D alpha, neighborhood of D alpha goes to H1 of S, goes to 0. Okay, well, what is this? This is the nil 3 manifold. And what's its homology? So you have the H1 of M intersect N of D alpha is Z squared plus some finite group, which depends on this K. And H1 of the neighborhood of D alpha, this is just a neighborhood of a torus. That's Z squared, so then you just stare at this exact sequence and you're done. So an idea that has become really enticing to me recently is that if you can understand which projective surfaces appear as smooth toroidal compactifications, then you can say something about the Betti numbers of ball quotients. Now, generically, these are going to be general type surfaces that you've never seen before, but it's very interesting that there's some things of lower codary dimension where you can actually do some things. So what you see is that now, so what we have is that M, which I'll call Hirzebruch's, maybe I'll call it M sub H for Hirzebruch's ball quotient, is a smooth, open ball quotient with B1 of M equals 4 and 4 cusps, otherwise ends. Okay? So here's some things that you can notice out of this. So let's let M prime to M be finite tall abelian with group G. So what that tells you is that there's some homomorphism, pi1 of M to G, but what I told you over there is that that factors through the map onto pi1 of B. B is up there. And so what you see is that M prime has smooth toroidal compactification, a G, a tall G cover of B. So it's an abelian surface. Blown up order of G times. Okay? And so what you then see is that B1 of M prime is also 4. And varying the group G, what's that? B, it's the same one up there. B will never change. The top board will stay up there and its notation will not change. Yes. Yes. I guess maybe I put an H on this. So what's the motivation for this? To me, it comes from Betti number cusp contributions to Betti numbers. So if you look at the Betti number of some quotient to the hyperbolic plane, this is greater than or equal to the number of cusps minus 1. It's an easy exercise. What's not that much harder is if you have a hyperbolic 3 manifold, the Betti number is greater than or equal to the number of cusps. And you know, like I said before, in the study of locally symmetric spaces, finding out exactly what geometric pieces inside the manifold contribute to its Betti number is an important problem. It's relatively elementary in these cases. But what you can now show, varying this G implies there exist towers of ball quotients with either B1 uniformly bounded and the number of cusps goes to infinity, or B1 and the number of cusps uniformly bounded. Which is very different than the behavior you see here. And the point is you just need to pick the right abelian group for those surfaces, and you count the number of cusps by the index of one cusp group going into the image, and it's all some simple covering space theory from there. I'll mention that using covers of Deligne-Moss cell overfolds, you can find some other behavior. So you can also get that B1, so you get towers. M sub j of bulk quotients with B1 of mj and number of cusps linear in the covering degree. And also using arithmetic techniques, and this is work of Simon Marshall, plus a very, very small epsilon. You can also get that the degree of M1 to Mj to the alpha grows less than B1 of Mj, and the degree of M1 going to Mj to the beta is less than or equal to the number of cusps. For 0 less, you can get intermediate growth types as well. So what you get from Simon's work is you can get alpha is, where did I put my sheet? 3/8 and 5/8? 3/8 and 5/8. So basically what this is telling you is that the relationship between the Betti number and the number of cusps is not as rigid as this case at all. Basically anything can happen. Okay, I can't tell you all the possible alphas and betas, but it's anything is game, basically. Halfway there, huh? Okay. Very good. All right, so what are we doing here? So we have a bulk quotient. MH with, this is B2 mod gamma with first Betti number greater than 0. It's in fact equal to 4. So that tells you that there's a representation rho from gamma onto z. Deep fact. Now, in fact, there's lots of them. And what I'd like to discuss now is a bit about the kernels of these representations. Yeah, so the Betti number grows. In fact, these are both the precise growth type, actually. The growth type of the Betti number is the covering degree of the 3/8. So it's growing more slowly, but at a definite 3/8 rate, and the number of cusps. So this is for congruence covers of arithmetic lattices. You get these growth types. So this is related to these conjectures of Sarnak and Jouet.
What is the rule?
It's just a represent. Well, so if you have positive first Betti number, then you get you get representations from the fundamental group onto Z. Right. So it's just one of them. And it's all just factoring through including this into that ball quotient and then mapping that 4 torus blown up, blow it down, map it to a circle. That's really, so in fact, you can find in that picture up there explicit generators for the homology groups, just out of the 4 torus picture. So my interest in this comes from 2 directions. And so it's the theorem of Stallings that M is a compact three manifold. Maybe I should assume prime and irreducible, but I don't think I have to. There's an assumption in this paper, but I think it was just to avoid the Poincare conjecture. And you have rho from pi 1 of M to Z, then rho has finitely generated, which implies in this case finitely presented, kernel if and only if rho is induced by a fibration of M over the circle. So this geometric property of coming from a genuine, and this is algebraic geometry, so you have to put on your topologist hats for a second. This has no singularities. This is an actual fiber, got out of this fiber bundle. So this is fantastic. This tells you that the group, the properties of the group are somehow telling you about the geometry of the manifold. And on the holomorphic side, this came up in Pierre's talk. I'm not going to state the strongest version of this, but there are at least 2 people in here that can give it to you if you want it. Say compact Kähler. We have rho pi 1 M to Z with infinitely generated kernel. By which I mean not finitely presented, because of course a finitely presented group is also infinitely generated if it's infinite. This implies that there's a holomorphic vibration of M over a hyperbolic curve. And I don't want to get into the intricacies of orbifold versus manifold on the base, but again, there's a purely group theoretic property that's and it was a bit of a folklore question, and somebody had conjectured to me years ago that these 3 amongst negatively curved locally symmetric spaces, I won't name him because I'm about to show that he's wrong. It was in private, but oops, I'm pointing at the wrong thing. This theorem of Stallings, the 3 manifolds should be the only negatively curved locally symmetric spaces with finitely generated kernels to Z. And it should somehow be based around the fact that geometrically 3 manifolds, by work of Thurston, about 15 ellipses, and then recently Agel, basically every hyperbolic 3 manifold you can build by taking a fibration over the circle and then taking a quotient of that manifold. And that should not be so easy in higher dimensions. But the theorem is that there exists, this is an observation, gamma is pi 1 of Hirzebruch's lattice with finitely generated kernel, and Now the board comes down, so I can draw one more thing. And so what you notice is that there's a nice fibration of this over a 2 torus. With fiber, a thrice punctured 2 torus. And it's just induced by blow this down and then project onto the first factor. And then there's some worry here about this 4 punctured sphere instead of a 3 punctured torus, but that's not a problem. So the proof is you use the above fibration plus a lemma from Norrie's paper on the Zariski conjecture, which says that you get rho hat from gamma onto z squared, which is pi 1 of the base of that fibration, with finitely generated kernel. And then this is an exercise to complete the theorem. So, okay. Maybe it's a bit bold to call it a theorem, but that produces an explicit example. I'll state something a little more, it's sort of off theme, but there is something more you can say, which is that for all gamma in PUN1, arithmetic of so-called simple type, this just means it comes from a Hermitian form rather than some more complicated division algebra. Then there exists gamma prime and gamma finite index. I'm going to assume co-compact, though it's not really necessary. I haven't checked the details in the quasi-projective case, but I'm almost positive they're right. Finite index. And rho from gamma prime to z with finitely generated kernel. Now, unlike the Stallings case, all of these are infinitely presented. They cannot be finitely presented. And that's just a Morse theory argument on the abelian cover. In the interest of time, I won't talk much about this. I guess to my knowledge, and I assume somebody in the audience will know, to the contrary, these might be the first negatively curved Kähler groups with this property. But that might just be because nobody asked Thomas yet. And so, I don't know, do you know an example? I'm looking at you. Thomas does that. If anybody, I didn't know any previous examples. If you don't, then I'll assume they're the first. And they also produce, the kernels of these produce geometrically, this is a little less interesting to this audience, geometrically infinite groups with limit set the entire boundary at infinity of the n ball. I believe these are also for n greater than or equal to 3. This is new. For n equals 2, you could have used fibrations of Deligne-Mostow examples.
Wait, I have a question. So
Yeah.
if you take, this probably will work only in dimension.
Oh, maybe it's, no, it's new for at least 4. Yes.
Then you have homomorphism like this.
Yes. Yes. The proof of this is not. Now, I don't know an example that fibers in two different ways, but the proof is along those lines. So the ingredients are.
What do you mean by fibers in two different ways?
Two non-homeomorphic fiber bundles.
No, I mean two different.
Yeah. So the ingredients to prove this are just right. You just need to make sure that there are some one forms that don't wedge to zero, and Clauzel produced those in the late 80s. So the proof is not, again, not. But I want to get back to Hirzebruch, I think. Well, so there are some other examples of these fibrations. So this so-called Cartwright-Steer surface also has finitely generated kernel. But so something that really tempts me, I'll only say this out loud, is whether this is actually giving fibrations of these ball quotients over, say, an elliptic curve, and that these fibrations could be some analog to virtual fibration. I mean, this is just complete pipe dream and is probably completely wrong. That's why I'm not going to write anything. But there's this Cartwright-Steer surface, which is a surface with PG equals Q equals 1. It's a ball quotient. It fibers over an elliptic curve, fits into this finitely generated kernel to Z plus Z picture. And it's curious. So now, basically, this theorem says that these homomorphisms with finitely generated kernel are generic. And given that they're generic, you could hope that maybe there's some sort of fibration over abelian varieties, elliptic curves picture for these compact ball quotients, but who knows? It's for somebody smarter than me to decide. Okay, so the last topic I'll talk about is the uniqueness. Of Hirzebruch's example, and the rest of this will all be joint with Luca Di Cerbo. And so I believe it's up there. Maybe it got erased. So we had that the Euler number of this Hirzebruch example is 1, which implies that it's a minimal volume ball quotient manifold. And this is just by proportionality. It has the volume is proportional to the Euler characteristic, and the Euler characteristic is an integer. So there you go. And the theorem is that there exist exactly 5 manifolds M and this is the critical ingredient. I know more examples. There's an old paper of mine about 8 years ago or so where you can find examples of manifolds that have Euler number 1 and don't fit into this picture. And have minimal volume. There's Hirzebruch. And then there are 2 bielliptic surfaces that admit 2 distinct realizations as the smooth toroidal compactification of a ball quotient. And these are all commensurable. So they share a common finite sheeted covering. So the lattices in the ball are all arithmetic and so on and so forth. Let's see. So I want to, so there are a couple more consequences that there's some sort of other fun facts that Luca and I extracted from this. You see, the trick that I was using up there, you can use the Albanese fibration. Of the bielliptics to show that there exists a gamma in PU21 with infinite abelianization and commutator subgroup that's finally generated. And so you just apply the ideas I had used previously, but now the fibration gives you the entire kernel. So up to finite index, actually, but OK, there's a little bit of fuss. The other thing is that for all, and this is the American natural numbers, so no zero, there exists a smooth projective surface. Oh, these are also blown up at a point, sorry. And such that Sn admits at least n distinct realizations as the smooth toroidal compactification of a ball quotient. And in fact, you could have used Hirzebruch to do this. And you just have to find, you have to do the covering space theory carefully enough so that you make sure that the ball quotients are not homeomorphic or isomorphic, but that the compactifications are, in fact, biholomorphic. And I should say that there's been some previous work on questions like this. Holzapfel thought about this problem and produced a larger volume arrangement of elliptic curves on a product of two abelian varieties where you use z adjoint I instead. And the key thing that seems to have been missed and that ends up being the real pain in the neck in our paper is that singular elliptic curves end up becoming key on these bielliptic examples. And I think that's people either neglecting or being too afraid to work with also looking at singular curves is probably why these hadn't been found yet. But somehow I knew that some existed. And Luca and I started talking, and he was like, I think this one's unique. There's nothing else. And I was like, I know I have at least 4 others. And 24 pages of calculations, and could I dimension 0 later, we classified them all. So in fact, yeah, all of these appeared in some paper of mine, but without the geometric description. So what I'd like to do to end is give a bit of the sketch of the proof, and then spend some time explaining a couple of these examples in detail and giving roughly the picture that you see. Some method. And so somehow, from my background, this is very appealing to me, because if you start thinking about hyperbolic 3 manifolds, you want to draw one and think about it. Well, okay, you can just draw some. I hope that's a link. I I think that's a Whitehead link. You just draw this and you have a geometric picture and you can play around with it and try to understand covering space theory and try to find geodesic submanifolds. For instance, you can prove that that exceptional divisor becomes a 4-punctured sphere inside that complement. You can prove it's totally geodesic using Hirzebruch proportionality. So you can actually start seeing geodesic surfaces sitting inside, or curves, or however you want to say it. I have no idea why I ended up on that tangent, but anyways, some about the method of proof. So step 1 is to restrict the Kodaira dimension. So we have this M, which is B2 mod gamma. And we have Euler number of M equals 1. So let's let S be the compactification and then you have S min, the minimal model. So let's start off with an easy case. Let's assume that the Kodaira dimension, this is a kappa, of is equal to 2. You see, the Euler number of the minimal model, so I've blown this up some number of times, is the Euler number of S minus K for some K. But this is general type, so that's positive. Right? That's just C2. Okay. Well, this is equal to 1. I've just added a bunch of tori to get this. So this is equal to 1. 1 minus K is positive, so that means that. And C2 is equal to 1. But you also have that K S plus D squared, this is C1 squared of SD, is equal to 3. But adjunction tells you that this is KS minus D squared. This is positive. So then what you see is that you get that 0 is less than C1 squared of S is less than 3. But 12 divides C1 squared plus C2. So you're done. So similar, it's even easier. So if you have a Kodaira dimension of minus infinity, you can reduce to the case where it's a P1 bundle over an elliptic curve. And similarly, for Kodaira dimension 1. And so now you're just in the case. And of course, if you have kappa equals 0, that implies the Euler number is already too big if you're a K3 or an enriched case. Right? This already has Euler number 24, and then I'm going to blow it up a bunch of times. So that's not going to ever give me something of Euler number 1. Enriched case has 12. Yeah, 12. So then you're just left in the case of looking at bundles over elliptic curves. So at this point, you've really whittled things down, and in various cases, you use various techniques, looking at singular curves and studying singular elliptic curves, because we're going to blow up this S. You want a smooth elliptic curve once you've blown up, but now this the point is the S you get now in this case, this has Euler number 0. So to get Euler number 1, you're going to blow it up once. So the point is you're left looking at the case where you have this P1 bundle over or you have a genus G bundle over an elliptic curve in various Kodaira dimensions. You've blown it up once. And so in the smooth elliptic curve configuration on S, you could have a singular point. And this can go. I'll give you an example to show that this singular behavior is actually a real pain in the neck for a reason. It's because it actually occurs. So here's a couple of our new examples. So I'm going to take Y. This is going to be a bielliptic. So this E is still that E. And so phi of W comma Z is so you take that map. So that gives you, right, so you're acting, so the point is you're going to get a smooth, for those of you that haven't seen these bielliptic surfaces before, the point is you're going to act by complex multiplication on this one. That has fixed points, so the quotient won't be smooth. So I throw a translation over here. And now this is a smooth quotient. So this is a bielliptic surface. So they're all cyclic quotients of products of elliptic curves. They were classically classified in terms of the group. And okay, so I'm going to take C1 on Y, which will be the image, I believe, of the diagonal, of W equals 0. This is the fiber of the Albanese fibration. Of Y. So now this only has one map to an elliptic curve. So its Albanese is a fibration over an elliptic curve, which is an easy exercise out of this picture. So the first curve will be the image of W equals 0. So that's the fiber of the Albanese fibration. C2, so that's smooth. C2 will be the image of the diagonal. And what you notice is the diagonal is not preserved by this. Okay, you have to do some calculation, but it's not that hard. So it's also the image of two other curves intersecting in a point, which I'll call 0, 0 because it's the image of 0, 0 up in this abelian surface. So this is singular. Right. So now inside of Y, we have C1, we have an Albanese fibration over E modulo translation. And then we have this other curve, C2, and here's the origin. And I'm going to blow up the origin to get, I don't know, let's call it Z. And the DI be the proper transform of CI. So D1 squared is -1, but D2 squared is -3. And to finish, right on time, so what you check now is that C1 squared of ZD is equal to 3 C2 of ZD. And you check that KZ plus D is Simpson. And so this is a bulk quotient. And it's, you can actually trace through the covering spaces to see that this is commensurable with Hirzebruch's example. You can really do it by hand and see the commensurabilities. So I'll just quickly give example 2. So this has another fibration over P1. So this Albanese fibration comes from projection onto, I'll get it wrong, this factor. Projection onto this factor descends to a map to P1. So you replace C1 with a fiber of Y going over P1, and you get another ball quotient. You get a distinct, you get a new. So that's 2 of the examples in this theorem. And you see that it actually gives, so one surface actually gives 2 distinct ball quotients. And that's it.
So if there are questions, please take the microphone to ask your question.
If you go to higher dimension, like
other
balls in higher dimension, then is there any ball to use the current classification? Did you hear or not?
I think the internet couldn't.
I just say that if you take instead of the 2 ball, like the 3 ball, do you think that classification of threefolds can be used also so easily to classify this type of questions?
So no, that's actually a fantastic question, and when you write your notes this small, you miss points that you wanted to raise. So there's recent work of Di Cerbo's squared and Baker and Zimmerman that says that these smooth compactifications, in fact, you don't even, I think, need smooth. If I'm upgrading their theorem, I apologize, but I think you don't even need smooth. They're of general type. So this phenomenon of having a smooth toroidal compactification of lower Kodaira dimension seems to be really, really specific to dimension 2. And somehow there's some higher rigidity happening as you get into higher and higher balls. So I think it's actually an interesting question to classify which surfaces not of general type can fit into this sort of picture. I think it's actually an achievable problem to give a full classification. Thanks for asking that. Somehow the point in the Baker-Zimmerman and Di Cerbo squared is bend and break, which doesn't happen here.
Other questions? If not, thank you again.